Great to see all of you. There we go. It's so fantastic to see all of you, and I'm really excited to share a bit more about ispace. And
yes, we're super excited. I mean, as I explained, I mean, this is a group of dozens of students from most of Latin, or several countries from Latin America, a couple from Europe, and I learned about ispace in different ways, different interactions that we had initially through Satellogic, one of our partners, particularly with David Vilaseca, but then also through the participation that you guys had at our class at Wharton. And I was struck by sort of the ambition of what you're doing, and I think that it's very much in tune with the kinds of missions that we're thinking about as well, and I see a lot of complementarity. So I mean, just to I mean, you'll talk about the company, but just to briefly introduce you, Marchel Holle is the lead of U.S. government relations at ispace Inc. in the USA. Before that, he was managing of Washington, D.C. operations for the Space Foundation, and also a research associate at the National Academies of Sciences and Engineering and Medicine, with focus on space studies. So he's very knowledgeable about these topics, and as I said before, he's working on the frontier of space exploration, and we're very much looking forward to what you have to share with us. So welcome, Marchel.
Thank you so much, and thank you, Ignacio. It's so great to see all of you here. So we're from, as Ignacio said, we're ispace. What you see in this initial lander here is our mission 2, which we're planning for 2023. So you see our rover. This is our rover Cerato, which is disembarking from our arm here, and it's going off to explore the moon's south pole. So ispace is a global company. So we have 3 main offices. We are a Japanese company. We're based out of Tokyo. That's where our headquarters is, and that's where also the assembly of our first lander, our mission 1 lander, is taking place right now. We also have a substantial presence in Luxembourg, and that's we have an office that's very much focused on space resources and space resource utilization. And then we also have our main office in the United States here in Denver, Colorado. Well, excuse me, in Denver, Colorado. I'm actually based in Washington, D.C. at the moment. So as you can mention, it's really fun to find those times. As you all know, being internationally minded, find that where do the time zones align between Luxembourg, the United States, and Tokyo. We currently have around 140, 150 people right now. About 70% of our company is engineers, but we have over 20 nationalities that are working for us, because we think here at ispace that space really is this global vision. It really crosses international boundaries. It's a world. It's a you know, the world is reaching for the moon. I think when you look back historically at these major space races from the 1960s and the 1970s with Russia and the United States, we saw a lot of nationalism associated with it. There was this desire for the United States, for America to be first versus the Soviet Union. And I think this is a different era. So collaboration is very important. We saw we saw collaboration increase through the last half of the 20th century with the Apollo-Soyuz, with the International Space Station. But I think that has really just been the beginning of it. And I think here, from the U.S. perspective, the Artemis Accords is a really important step towards bringing in members of the international community together on this global vision. So here's a bit more about our presence here. So again, we have some key strategic partnerships with NASA. We work a lot with the European Space Agency. We work a lot with the Luxembourg Space Agency, and we work a lot with the Japanese Space Agency, JAXA. So we're in close contact with them. I'm grabbing coffee with them tomorrow, and we'll, you know, we talk about ourselves. We very much coordinate our messaging here. And here is basically our vision. So our vision we call Moon Valley 2040, and this is something that has been touted by our founder and CEO, Takeshi Hakamata. And Hakamata-san believes that we as a society, or as a global unit, need to have a long-term connection between the Earth and the Moon and create a Earth-Moon commercial ecosystem that will allow us to prosper. And we call this Moon Valley 2040 because throughout history, valleys have been sources of inspiration, sources of, economic innovation and inspiration. So we look at the cradle of civilization in the Indus River Valley. We look at Silicon Valley in California, and we see that valleys tend to be these places where people live and they share different ideas. Now, if as you are all kind of students of space, you'll note that in reality, we're probably not going to settle on a valley on the moon because of the darkness in these valleys. So in true point of fact, the best place to settle on the moon are these places near the South Pole called the Peaks of Eternal Light near Shackleton Crater, where you see near constant sunlight. So it's more of a metaphor. But we still like to tout this this vision. And here's just a quick, we'll see how the video translates here.
The universe's newest city is home to 1,000 people. And every year, over 10,000 come to visit. Only 20 years ago, this city didn't exist. It's the result of pioneers sending rovers, then discovering water. The hydrogen and oxygen separated from water becomes energy, creating the foundation for a fuel station. And with the fuel station came scheduled flights, followed by settlers. Soon, settlers required more diverse skills, attracting new specialists for construction, steel, communications, energy, transit, agriculture, medicine, and more. People travel from far and wide to see this new city. We call it Moon Valley. The moon is the new staging ground for your next level business. Expand our planet. Expand our future. ispace.
So that's our vision for all this. Let's see if I can click to the next one. So how do we do this? Hold on one moment. Okay. So how do we do this? So ispace, unlike a lot of our competitors in the lunar ecosystem, is very much focused on in situ resource utilization, or ISRU. We are very interested in the exploration, the prospecting for, and the processing specifically of water ice, but also lunar regolith. So lunar regolith itself is quite dry, as you know. The moon is a very dry place, and some of the destinations we're going to in the near term are even drier than other places on the moon. But at the South Poles, we see a lot of we see the potential for water ice. So you see here, there was an experiment that was done by NASA called LCROSS, in which an impactor was sent to the South Pole. It basically was a bullet fired at the moon. It created a plume of ejecta off the lunar surface, and that was analyzed to see the percentage of water in the plume. So we have proof that the moon is loaded, especially at the poles, with water ice. And this water ice is important, obviously, because if we can sift it from the regolith, we can turn it into drinkable water. We can also use electrolysis to turn it into oxygen for life support. And then also through electrolysis, we can create rocket propellant for hydrogen and oxygen engines by obviously splitting the water into H2 and O2. And so that is the 6.6 billion tons of H2O that we've found. ispace we think that in order to find this water ice, we can't just have a couple of large landers. We need to have a lot of different smaller landers that have different prospecting robots that are able to go out and uncover high probability veins of water for which we can send larger robots down to harvest and to turn into this, this rocket fuel. So, but the moon is not just rich in water, it's also rich in a lot of other resources. So we can identify high degrees of iron, of magnesium, of aluminum, of silicon, going up into rare earth metals. So there's an element that's pretty, that's quite prominent on the moon that's called creep. And that stands for potassium, K, platinum, P, and then rare earth elements, so creep. We also see a huge amount of titanium inside the regolith, as well as a wide variety of elements. And this, as you can see, as I flip through this, this shows the different heat maps of different elements on the right. So you see where we have like a lot of ferrous concentrations, the presence of iron, as well as the presence of these other elements that's differently mapped out. So we are currently in the talks with a lot of different payload providers that are looking at processing this regolith into, so one, for example, can process the iron in the regolith into steel. Another one can process the aluminum into the regolith into ingots, and that aluminum can be used actually as propellant for a new type of deep space engines that actually essentially send an electric current through the aluminum. It strips off the atoms and it fires that, uses that as the reaction mass instead of conventional propellant like hydrazine or hydrogen oxygen fuel. So one of the advantages to this, why we should be doing this, one, I think at ispace we believe it's important just prima facie, so at the first, for humans to be living and working on the lunar surface. We think it is preferable to live in a world where civilization is prospering on the moon than a world in which civilization is not prospering on the moon. But we want to do it responsibly. But we also want to use the moon as a stepping stone to other destinations in low Earth orbit low Earth orbit, deep space, and beyond to Mars. So because of this thing called the tyranny of the rocket equation, it's very, very costly from a physics perspective and from the monetary perspective to lift fuel from Earth because there are gravity losses. So as the more fuel you bring, you need fuel to carry that fuel, and you need fuel to carry that fuel, and so on and so forth. So you quickly reach an exponential function. If we are able to have water ice on the moon that we then refine into the hydrogen and liquid oxygen, we're able to launch deep spacecraft that could take dozens, if not hundreds of people to Mars, and we're able to refuel them in lunar orbit at a much lower cost compared to other mechanisms. That really simplifies the architecture, and it allows us to have a lot more trips out to Mars. We also see a business case for the refueling of geostationary satellites in the GeoBelt. So communication satellites are a huge economic driver of the space economy at the moment, but they're very fuel limited. And one of the economic sectors that we're tracking very closely is on-orbit servicing and refueling. These are robotic spacecraft that can dock with larger geostationary satellites, and they're able to service them, they're able to make repairs, they're able to refuel them, but they need to get that fuel from somewhere. So we're talking with companies that are interested in developing orbital depots that we could take our water ice, prospect for it, mine it, collect it, and then shoot it into orbit on low-cost, reasonable transportation. These depots then travel from cislunar space to the GeoBelt, refueling these satellites. And there has actually been some business cases that have been done by folks, specifically at the University of Central Florida, that prove that a very modest ISRU facility, perhaps on the order of only a few metric tons, is able to become profitable in this servicing model. And then finally, and I'm doing this in a bit reverse order, finally, the lunar resources are important to build infrastructure. So we would like to have a moon base on the moon. It's impractical to bring all the modules from Earth. So instead, to deal with the hazards of the moon, such as the micrometeorite environment, in the space radiation environment, it's a much more attractive proposition to use the regolith on the lunar surface to actually to build things in situ. And so that helps us create this road to Moon Valley. So our first phase, what we're working on right now, is a series of lunar landers, and we want to establish a rapid cadence of landings at the lunar surface. So we are backed, just as a kind of a business side, we were backed by around $130 million in venture capital. So we raised our initial round in 2017, a $95 million raise, and then finished a second raise last year for another additional $35 million. We're taking that money and we're building a lander service that creates frequent transportation to the moon. We then want to establish a water exploration system in which we prospect for this, and then we sell that information or to other perhaps larger concerns that are able to go and exploit that information, and then also ally with strategic partners for hydrogen energy. So, for example, we are in current negotiations and talks with Air Liquide out in Europe, and they're very interested in learning more about hydrogen fuel cells on the moon and flying perhaps a hydrogen fuel cell payload. So what ispace does is we do everything inside the blue box. So we contract for a launch. We currently are using SpaceX. So we've bought 2 SpaceX launches and we're contracting for a third. Although this is not a Falcon Heavy, it's a Falcon 9 reusable. We then build the lander, we conduct the lander navigation, the landing, and then we also build rovers, mostly from our Luxembourg office for rover exploration. We then acquire data, which is where the water is, and that really is our product. So at the end of the day, ispace sees ourselves as a data service company, in addition to being a lander transport provider. So you see, here's our lander. This is called Hokuto R. So Hokuto R is it's white rabbit in Japanese. Hokuto is white rabbit in Japanese. So in the United States, we see culturally a man on the moon. In Japan, and they see a white rabbit, the rabbit on the moon. So that's a kind of a symbolic nod towards our Japanese heritage. Hokuto R has a payload capacity of 30 kilograms. So it's not a lot, but it's still, for proving the market out, we think it was important to start small. We also are developing a second rover. So this is a rover called Serato. Serato is a lunar rover that's designed to take a payload of 5 to 10 kilograms. And we expect that to survive for about 1 lunar day. So about 2 weeks. We're also developing a few other rovers. One is a micro rover that has a payload of 1 kilogram. And the other is a larger rover we're calling an exploration rover that will also have a payload around 7 to 10 kilograms. And we control all this from our mission control center. So this is kind of a preview of what it is. They're currently in the finalizing its construction, delayed a bit with COVID in Tokyo. So this is our MCC. It's in Tokyo, Japan. This is where all the instructions from our different payloads will come from. And we also have a backup center, probably in the United States as well. And here is our lander. So this is the Hokuto R landing sequence. I hope this stuff translates over the connection.
Going to the moon comes with significant challenges. The Hokuto R lander must withstand intense vibrations during launch, as well as the harsh environments beyond Earth, the extreme temperatures, the vacuum of space, and radiation. The lander has 2 propulsion systems. The propellant tanks feed fuel into the main system, generating thrust, with the assist thrusters pulsing to adjust course. The RCS system modifies the lander's orientation. The lander is equipped with highly reliable guidance technology. The sensors measure the speed and distance to the lunar surface to perform an autonomous landing. Lunar imagery captured by the lander can be used for research and development. The landing gear is designed to absorb the impact of landing.
The lander can carry and deploy rovers, which are able to explore the lunar surface. It can also transport scientific instruments, cameras, and other payloads. The payloads receive power from the lander, which utilizes solar energy. And the lander's communication system remains in contact with Earth throughout the mission. Landing on the moon in 2022. Octo R.
So that's our pride and joy at the moment. So they're currently in the midst of building it. So here are some pictures that we're able to share. So you see, unlike we're really glad to say that because of our venture capital raise, that we're able to procure these long lead items. So you see, this is a carbon fiber. It's called a carbon fiber monocoque structure. You see the thermal insulation of the fuel tanks, the propellant tanks on the bottom left of the lander. So these technicians, they're practicing something called the sleeving operation. So the lander is made in three main components. You have the top part, the payload bay, the main body of the lander, and then the landing legs. And so it's important to sleeve these together and ensure everything fits and there's clearance for it. As you saw in the animation, the payload bay of the lander is about where the heads of these technicians are, and they're able to. That's where we're able to deploy the rover out. And so now we're able to say that we're proud that the first mission is the first rover that we're going to deploy is the Rashid rover from the United Arab Emirates. So it will be the first Emirati mission to the moon. It will actually be the first ever mission from any Arab nation to the moon, and I believe that makes UAE the 5th or 6th nation to land on to be part of a lunar mission as well. So along with the UAE Hope probe, which recently entered orbit around Mars, this is a huge part of the UAE's plan for space exploration moving forward. So then, as I described, we are going to use these rovers similar to the Rashid rover to identify this water ice in the permafrost or this permanently shadowed regions, and then sell that to other companies that might be interested in using that. So we've done a pretty extensive market analysis, as you can see. So we firmly believe that lunar activity on the moon is going to pick up substantially, and we see thousands and thousands of demand, at least, for thousands and thousands of metric tons. Now, the key is identifying enough of collections of it to make it useful and to make it kind of worth our economic while. And as I mentioned, we eventually intend to use this as a base, a stepping off point for deep space exploration and lunar supply. So while it seems so foreign and distant that the moon we haven't gone back in 50 years, we do think it is really just the stepping off point. And we really are going to hopefully see a golden era of human exploration and activity here, in which we'll look back on hopefully in decades and see that this is where it all really began. And we envision a world in which we have Mars colonies and moon colonies and long duration missions to the other planets. And it really comes from here first. And it also comes with all of you. So as you are starting to work to look at this, there has never been a time more conducive in human history to really escaping Earth orbit, having humanity go out into the stars as part of a true international coalition. And I think we all are living in very lucky times, and we're all very fortunate to have an opportunity to be part of this. So with that, I'm open for questions. I'm open for discussions. This is maybe I'll just leave it on this. Here's our at a glance slide, but I can jump back to anything or answer any questions.
This is
I tried to look at the chat and I paused the video, so let me go to that. Oh.
Fantastic. This is extraordinary, Marcel. Thank you very much. It provides a very good overview of what you're doing. It's amazing, and it's very consistent with what we're seeing as well. We think that the cislunar economy is going to explode, and probably not enough attention is being paid to this opportunity. We want to just be a little part of it and try to show to people, particularly in emerging countries, but also particularly young people, that they can be part of this incredible revolution and this incredible adventure. At the same time, incredible business opportunity. And we think that this begins with exploration, and this is enabled by companies like yours that enable sort of the access to the moon, which will be a major, I mean, it's clearly the biggest obstacle right now. I'm curious if you could explore, I mean, I'm sure that there are many questions in people's minds, so I don't want to take too much time from their questions, but I'd like to ask you, what do you think are the roles for rovers? What kind of interesting missions could students be thinking about for their rovers? And also for CubeSats, what kind of things do you think that could be interesting to do? In one case, that cannot be done from a satellite, and I mean, what can be done on the ground that cannot be done with a satellite, and in the other case, the opposite. And also, if you have any considerations in terms of what do you think will be the first kinds of habitats, human habitats, that will be required for the settlement and the exploration, the human exploration of the moon?
Excellent, Ignacio. So I'll take that in, and thank you for that, and I'll take it in reverse order. So I think one of I think initially we'll see a lot of prefabricated habitats. I think the initial modules are going to be place a high degree on reliability, but eventually I think the big change is going to be using the lunar regolith itself for these habitats. So that's a huge difference from these deep space missions to the moon, and it's a huge advantage to the moon. So cosmic radiation and the radiation challenge is a massive problem. It's a massive problem for Mars exploration, and it's also a problem for any deep space exploration. So because the International Space Station orbits so close to inside Earth's magnetic field, we're largely shielded from the bulk of the ISS astronauts are largely shielded from the bulk of galactic cosmic radiation, although that is still quite relatively high compared to our experience. For Mars transits, it's extremely high. And in some ways, the more you try to block it, the worse it becomes, because you'll be hit with these high energy particles, these cosmic rays. Those rays, almost like a bullet or a shell fired at tank armor, will crash into the outside of your spacecraft or your shielding, and will split off a shower of secondary radiation in the form of gamma rays. So you can almost, these rays, by shielding yourself from this one type of radiation, you can almost make another type of radiation even worse. So the moon is a big advantage because being on the surface, you have half the radiation exposure already because you have the moon under you. And you also have a lot of regolith that you can start piling up and creating these larger, more fortified places. Another thing that I think is a really interesting part for habitation is the prospect of lava tubes. So on the moon, we can see these riles, these volcanic vents that occurs from lunar activity. And it's quite possible these vents are kilometers in length that just extend underneath the lunar surface. And you could completely see, by just walling off one wall of it, you could create a massive underground complex that thousands of people could live in. And I've actually spoken to some folks quite recently who are interested in using these tubes as a genetic ark. So they are interested in landing near one of these vents and then having rovers or astronauts, if we have a large enough lander, explore the vents and then put a guide wire on top of the vent and then lower down thousands of tons of seeds collected from all over the world, similar to the Svalbard seed vault near the Arctic Circle. Of course, in the lava tubes, these would preserve for perhaps billions of years. It actually would be the longest lasting genetic ark that you could really, that you could ever have. It would be a massive monument to humanity. Going to CubeSats, I think there's tremendous opportunity for CubeSats. one of the things I would look at specifically, or one of the interesting areas of exploration is the magnetic anomalies at Reiner Gamma. And there are some other magnetic anomalies that are throughout the lunar surface, but it really is important to get close and pass through the magnetic fields emanating from these spots on the moon. We don't really know why there are these strong magnetic fields at the moon, but it's important for us to have a lot of different observations that pass through these magnetic fields. A big issue with lunar satellites is that the moon is gravitationally very lumpy. It's very difficult to keep things in stable orbit, even without an atmosphere. So in some sense, it makes a greater degree of sense to do things with CubeSats that are cheaper, that you can afford to lose after a few months, than it is to have a much larger satellite that is constantly having to maneuver in low lunar orbit. There are a couple orbits that we call frozen orbits, that you're able to keep things there without having to move them around a lot. But you don't really get to see a lot of the more interesting observations. It's very restricted. When you're only restricted to 4 key orbits, you can't really explore the things you want to explore. The other thing I would bring up are communication relays. So if you wanted to test out different ways of communicating on the far side of the moon, that would be another interesting project for CubeSats to do, because we currently, while the Chinese have a lunar relay satellite, there's no way for us to talk to things that are on the far side of the moon to the near side without those relays. And then finally, for rovers, I think, in addition to our obsession with water ice, it's clear. Any geologist will tell you, and we see it in the Mars rovers, that just landing at a place doesn't give you the whole picture. You really need to see different areas of opportunity. You need to get up close to different areas. I think at the moment, just understanding how rovers can function in the lunar environment and how long can they function before the dust overcomes their mechanisms would be very interesting and useful as an experiment in and of itself. But we are talking to a few payload providers that are interested in looking at microscopic images of how does the lunar regolith lock together. So the lunar regolith is not like Earth dust at all. It's actually very sharp and jagged and spiky because it hasn't been weathered, or it hasn't been weathered by Earth processes. And so these lock together like, hard to describe it, that the grains at a microscopic level lock together in a way that dust or sand on Earth does not, because it's been rounded. So for example, it is if you were to pour regolith out onto the table, it would form a very steep tower that would just seem unnatural on Earth because it has a high angle of repose compared to other more rounded dust. And so understanding that is very important for future spacesuits. It tears up spacesuits, it gets inside joints. So we need to understand lunar regolith better. And because it is so unique, it's very difficult to replicate on Earth. And lunar simulant is, I would argue, it's probably impossible to properly simulate regolith. So it's important that we understand it much better.
Fantastic. So wonderful answers. There are questions coming in, and I'll ask the people who are writing them to say them out loud. So Marone, I'm not sure the first name. Please go ahead and ask your question.
Sorry, can you hear me?
Yes.
Yes. First of all,
would you
thank you very much
for your
for
camera, if possible?
Yes, I have had some trouble. Can you see me now?
Perfect. Yes.
First of all, thank you very much for the presentation and for your time. And I would like to ask you, how do you decide where to send the missions to? And I mean, I don't mean the South Pole in general, but like more precise the more precise location. And what kind of information do you use in the decision-making process?
It's an excellent question. So let me, for us, it's a negotiation with our customers. So we haven't yet set the exact coordinates for our missions yet. But one of the things that we take advantage of are the degree of reconnaissance information and photos that we have on the moon surface. So I'm going to put a link in the chat here. So has everyone ever used a quick map before, or LROC?
No.
So there is a link.
Mm-hmm.
This is run out of the Arizona State University. So this is essentially a high fidelity Google sets of data sets that have collected from almost every mission that has visited the moon that the Arizona State University has aggregated together in a searchable format. And you can zoom in on, just like Google Earth, onto any place on the moon, and will tell you okay, here's our data here that we have from our lunar diviner instrument or our M-Cube instrument. So we're able to really understand what are some interesting specific areas to get to. If you look at a mission, one of the missions that I'm currently thinking about is our mission 3, and where do we land to explore the lunar swirl at Reiner Gamma. So that means that the lunar swirl are a series of banded, it's different albedo. So it's an alternating series of light and dark bands of lunar color. And so because our rovers will probably not have a long life, and they won't be able to move very far, they're not able to move tens of kilometers. It's important for us to land at an intersection of bands such that we're able to, either from the lander itself, take spectral readings from a distance at the dark band and the light band, or we're able to deploy a small rover or two rovers to visit alternating sides of the band. But to answer your question, that's a negotiation with the science. You would have a science team that you would bring on board, and we would work through our payload integration process to decide, and have this negotiation with to ensure we have the highest science return.
Fantastic, thank you. So the next question is by Lucas Mariano Grigolato. Lucas, please present yourself. I mean, just explain what you study, where you study, and please state your question. Lucas, are you there?
Sorry, I thought I was on mute.
Yes.
Hello, I am from Argentina, like the rest of the guys, almost the majority. I studied at Balseros Institute in Bariloche, and I'm a telecommunications engineer. So I am at EE, the project EE, and I wanted to ask if the company is planning to use satellites for the communication between the lander and the Earth, the base station on the Earth, and if you consider to use optical satellite communication for the link.
So our initial landers on the near side will have direct to Earth communication with high throughput antennas using. We haven't decided yet exactly what is the exact service. We will need those. We will need relays for far side missions. So we are very interested in optical communication satellites. We're very heartened to see the optical crosslinks from, for example, SpaceX Starlink, and to see this become for years, people have been talking about optical comms, but it seems that in the past few years, it's become much closer to reality. I think early on, we would either use optical comms as a test demonstration, but we probably wouldn't rely on it as our sole means of communication until that's been more proven out in cislunar and lunar orbit. But it's interesting you bring up optical comms, because I think there's a pretty unique use case for the moon for optical comms. And that's because the far side of the moon is a pretty unique environment in that it is a radio quiet zone, unlike any radio quiet zone that is possible on Earth. So a lot of scientists have proposed about deploying large baseline arrays, radio telescopes on the far side in order to really see distant radio sources. And the other thing that helps is that there's no ionosphere. So there are low frequency radio waves that are blocked by the Earth's ionosphere and magnetic field, and you're able to get away from that on the moon's far side. And of course, as soon as you start talking about relay satellites and having all these satellites in cislunar space, you start polluting the spectrum with these radio waves. So I think eventually it would be interesting to see lunar communication be almost exclusively optical comms, so you don't have that problem, so you don't spoil the far side. Although that's, again, this is, I think that we're probably a ways out from there. I think we hope to see that in the near future, but I think that's kind of an interesting use case for it, and it's really unlike any other area that I can think of in that regard.
Thank you. The next question is by Sebastián Calvera. Sebastián, are you there?
Yes, hello, my name is Sebastián Calvera. I am a mechanical engineer, also from Instituto Balseiro. First of all, thank you very much for the presentation. And I want to ask you about, I saw that you're interested in tracing water and selling that information, but also you were planning to establish this Moon Valley. So wouldn't be like feeding the competition, your competition, to sell this information to another entity that would like to establish a Moon Valley, a colony like this?
So I think in the short term we are interested in finding and selling that information. I think we think the ecosystem will benefit from that. So at the moment, I think one of the things that we are cautious about is that, and I think I see in your question that you say, who are you thinking of selling it to? And that is a very perceptive question, and that's the question that a lot of people in the space community, I believe, don't think enough about. There is a supply chain that needs to be simultaneously, that different investments need to be made in different areas simultaneously to make this ecosystem close together. It doesn't make a lot of sense for us to find this water ice and process the water ice if the rocket engines don't use this as fuel. And so, for example, SpaceX would be an interesting example of this. So SpaceX's Raptor engines use methane. They're Methalox engines. They use methane and oxygen instead of hydrogen and oxygen. So it's not, and they do this for some very important physics reasons, but it's because it's designed for Mars in situ resource utilization, not Moon in situ resource utilization. We're still able to, we think there's still a business case in that where we're able to use or find the oxygen, but what we need to be thinking as a community, what it has to be able, everything needs to be able to do, everything needs to be able to lock together. So we see a future in which we're selling fuel oxygen to engines that use Methalox or H2 and O2 to engines that use Hydrolox. But you're right, you need to have these engines that are reusable, that are able to be refilled. You need to have cryogenic storage areas inside the permanently shadowed regions, because you can't store it in the hot sun. So all these things need to be happening. Key investments need to be made simultaneously across the value chain for all this to happen. If you get up there and we have, here's your tank of water, but there's no place to store it, well, that doesn't really work. One idea is to keep it in liquid form and then sell it to refiners in lunar orbit that would have sunshades that are able to better block the sun to keep these cryogenic fuels cool. But your answer is that there is no solution to this just yet. And this is a huge topic of debate in the community. I would wager that there are a lot of theories about how this is solved, but no answers just yet. But I think we think we don't need to have we don't need to have the answer to everything to not make these key investments moving forward.
Perfect. And something that I didn't share with you, Marcel, is that the winners of the last Space Up Challenge by NASA are participating in this competition, and Sebastian is one of them. He was one of the winners. So next is Daniel.
Hello, I'm Daniel Echearri, member of the team EE, and I have a master's degree in technological physics. I wanted to ask you if ispace is planning to develop a lunar transport system oriented to transport between different points of the moon. Not necessarily for astronauts, but also for robots that needs to be deployed at very distant points from each other. For example, I don't know, a 3D printer that will be used to build the infrastructure for a colony, and then you want to build another one in other place tens of kilometers away. So I don't know if ispace is planning to build that transport system.
So at the moment, we do not currently have plans for that. The initial plans are for lunar delivery. I think we are interested in maturing technology that could be used for perhaps like a high speed. Yeah, you mean more similar to? Do you mean deploying separate payloads in different areas, or do you mean more of a hyperloop or high speed rail line on the lunar surface? Yeah. So at the current moment, we are not looking at that just yet, but I think that will eventually become a key part of the lunar colonies moving forward.
Maybe something like spin launch, for example. Also, I don't know if
the spin launch stuff. Now that's a very interesting business. So again, the moon is a very unique place for a company like Spin Launch.
Exactly.
And for years, people have talked about things like rail mass drivers, or because you don't have to harden the payloads or for the G's that it's pulling.
Fantastic. So I can't see the name of the person who's after Marco Daniel Echearri. Please go ahead and ask your question and present yourself before.
I already asked the question. I don't know if there is something.
Oh, no, but after you, there's somebody and I can't see the name.
Yes, I'm sorry.
Okay.
First of all, good evening, and thank you for this great presentation. I am Emilio Mendoza, and I study mechanical engineering, and I am from Peru, and I am working with Space Bridge team. And I think that one of my questions has already been answered, but I'd like to know to whom would the moon belong when the first bases begin to be established, like in Moon Valley. I'd like to know that.
So very interesting question, Emilio. So under the terms of the Outer Space Treaty, no nation can appropriate the territory. So no one can own sections of the moon. Although I had a friend recently give me a deed to an acre on the moon as a joke. Nobody can own the moon as property, but you're able to, although you can't own it, you're able to. There's nothing prohibiting setting up a base or setting up an instrument or a lander or a scientific facility, although that is not necessarily, it's not as if that area around it, for example, around a US base, that wouldn't be United States territory, that would just be a US base on the moon, similar in a way to Antarctica. Although that's not an exact analogy. And I caveat all this with saying I am not a lawyer. One of the things that we believe is important, though, is although no one can own property on the moon, we believe it's important to be able to own lunar resources. Because if you're an astronaut on the moon, as living on a moon base, and somebody somebody has gathered some water or some ice for you to have, well, you have to take possession of that water in a way and be able to utilize it. And you have to be able to, in a sense, own the resources that have been extracted from the moon. And it's almost similar to we see in both the United States and China have both now returned samples from the lunar surface, and Russia is planning to do this soon. So although China or Russia or the United States doesn't own the moon, they certainly do own those moon rocks in a way that we would say is property. ispace actually has entered into a contract with NASA as of last October, and that in our first two missions, when we land on the moon, we're going to collect some lunar regolith, not a lot, just 50 grams, and then we're going to sell that to NASA for a small fee. Not that will pay for anything, but we believe it's important to demonstrate that that any successful effort to settle or use be on the moon requires the ability to buy and sell resources also on the moon. And so we think that's a very interesting legal precedent. But to answer your question succinctly, under the terms of the Outer Space Treaty, no one can own the moon.
Fantastic, thank you. I don't know how are we on time. I mean, the hour is close to finish. I don't know if you have a little bit of flexibility. There are several, yes or no?
Yes, I have flexibility. Yep.
Okay, fantastic. So let me invite then Juan Benzalon to ask the next question.
Oh, that's me. So I'm Juan Benzalon. I'm from Instituto Tecnológico de Buenos Aires in Argentina, and I'm with the Connecting Worlds team. So my question is whether the protocols that you use to communicate between landers and payloads and landers and Earth, whether they're proprietary or standard, and kind of hand in hand, whether like just out of ignorance in terms of satellite communication, like how realistic it would be for a CubeSat to communicate with the lander and or with the rovers.
Interesting one. So definitely, I can say that so I'm going to give a unfortunately not very satisfying answer. So because of where we are in the design process, we've our lander communication protocols we're currently not disclosing. I can say that there are standard interfaces that NASA uses specifically with payloads and also with rover to lander communication. So there is like Wi-Fi basically, and our intent would be to have standardization. So a lot of our competitors, Intuitive Machines, I believe they have an agreement with Nokia to fly some sort of LTE on some like 4G LTE stuff on the moon. I think we believe we want to have common standards because we think the market, it's hard enough to get your payload to the moon as is. It's even harder, we think, if you're trying to design it for a particular lander or a particular company, and that is just an additional step that we think is too onerous at the moment. Although, and I don't think I can unfortunately speak intelligently to your question about CubeSat to lander communications, as I'm not a comms engineer. I do know that. We think closely about like tracking and how much are we able to gimbal and given on different orbits, making sure we're able to constantly track a potential relay satellite is important to us.
Right. That's very.
Just out of consideration for Valen, who raised her hand before writing the question, Franco, I'm going to ask Valen to ask the next question, and then I'll come back to you. Valen, would you like to ask your question?
Hi. Yes, thank you.
Please introduce yourself.
So, yeah, I'm Valen. I'm studying physics at the University of Buenos Aires, and I am with the Stern team. My question was, so you talked about splitting water for refueling on the moon, and so where would you get the energy from? Would it be nuclear? Would you get solar energy? So yeah, how would you do that?
Excellent. Yeah. So we are currently looking at solar sources, and there has been a lot of discussion in recent years about nuclear propulsion, or not nuclear propulsion, but nuclear reactors on the moon. So NASA, for example, has a program called Kilopower that it looks almost like flowers on the moon. So a temperature difference is created between the hot radioactive material and the radiators on the top that are radiating into the blackness of space, and that's used to create power. Because of there are a lot of complexities in dealing with radioactive materials, and so that is something that we are currently not looking at. We think for the near term, solar will be enough. Of course, when you start looking at bases that are not located at the South Pole, it really helps to have a radioisotope source. I mean, it's just lunar night is extremely cold, so you get, as you know now, you get 14 days of sunlight, and then you get 14 days of darkness, and the darkness is very cold, and you need to have enough batteries in place to keep your payload alive during that intense coldness that will really freeze your device. Things get a lot easier if that is a nuclear power source, because you're no longer reliant on that sunlight.
Fantastic. Franco, next question, and please introduce yourself, Franco Sosa.
Hi, thank you for all. I'm Franco Sosa. I'm mechatronic engineer. I have studied my degree the National Luis in
Unfortunately, I think the connection is very, very poor.
Oh, sorry, I have a connection.
Yes, but not a problem, Franco. I'll read your question just so we can answer it. So the question is, actually, you have two questions. The first is how the rover is located on the moon, how it lands on the moon, and the second is how the weight is distributed inside.
So the rover for our first two landers is deployed from the top deck of the payload bay using an arm that deploys outwards passively. Our third mission, and one thing that I probably some important bit of context that I may have left out early on is that our third mission has a payload capacity of 500 kilograms. It's quite a bit larger. That's one of those things that you don't realize you didn't. So it's about half a metric ton. We're able to deploy a rover off the top using we don't use ramps, but we use other passive deployment system. But we're also able to deploy smaller rovers from lower bays on the lander with ramps. So that drops down, the rover drives away once it's powered on. Weight distribution is actually pretty important. So our engines are located, not just our engines, but any engines are generally located, we want to thrust to the center of our mass. So we need to do that very precisely. So it's important that when we talk about how do we locate payloads, that we balance everything so that we have, that we generally don't go off kilter. I'm not sure if anyone saw the Rocket Lab recently, but they thrusted off their axes, and that was the end of that. So it's important to have to make sure that everything is balanced.
Fantastic. And then Max Belmonte.
Yes, hi, hello. I'm Maximiliano Belmonte. I study biology at the University of Buenos Aires. And my question may be not in the area in which your company is right now exploring, because it's more related to a longer term stay, but I'd like to know if your company has already begun to think about crop growth with in situ material for first base, and what specific crops are deemed essential when trying to accomplish a basal diet for the first long-term stay on the moon.
So we have been looking at different crop growth experiments, and on the most recent Chinese mission to the moon, there was actually a cotton plant that they had they were testing do plants, so this is actually a big, an area of research that has not been, I think needs to be pursued a lot more. How do plants germinate and flower and develop on gravities less than 1G? So there have been some studies that do analogs on Earth, and they do this by taking the plant and they rotate it 90 degrees, and they spin the plant so that the net gravity over time is 0. There's some plant growth experiments on the International Space Station, but that's really not the same as doing the real thing. And so when we see the Chinese plant experiment that was, again, germinating cotton, we see substantial differences from, I'll have to find fortunately I don't have that handy, but we see pretty substantial differences in growth rate and development between that plant and then a control conducting on Earth. So we need to understand more about why that is. Plant growth is especially important, as you mentioned, for nutrition. I think we haven't thought about this too much from a moon perspective because astronauts will be resupply is so readily available. But when we talk about long duration Mars stays, where you're having to stay there for a period of years and have food that can last for the duration of an entire long voyage, which could be in some circumstances, extreme circumstances, 5 to 6 years, well, the vitamins start breaking down in the food at that long term. So you really need to have seeds and plants to grow these essential vitamins, especially at the tail end of your trip. I think, so I know there are people that are talking about that, who are talking about how do we adjust astronauts' diets for long duration space flight. Is not, unfortunately, not saying that ispace in particular has done work on, short of keeping up with some of the literature.
Thank you.
Excellent question.
The next question is by Tomás Bosqueto. Please, Tomás, introduce yourself.
Hello, how are you? I am Tomás, an aeronautical engineer. My question has to do with the sustainability or the prospects for sustainability of the exploitation in, let's say, 100 years, considering that I don't know whether you have feasible figures regarding the amount of resources that the moon crust possess. So let's say you have arrived on the moon, you have set up your base, you have begun resupplying ships and even manufacturing missions for deep space exploration. But do you really have the numbers and the figures that back the idea that this exploitation will be feasible in 100 years or 50 years or in the long term?
So we believe, while the evidence is still, so we believe, yes, that there is, we believe that the water is, there's quite a bit of water, billions of metric tons of water, such that, we think it's unrealistic to see ourselves, consuming that in the span of hundreds of years. I think to your larger point, I think sustainable exploration is important. So the moon, we want to be responsible while we do this. So, we think, but at the same token, we also don't want to make the barrier so high such that this never happens in the first place, because it takes perhaps similar. A lot of people talk about like Mars planetary protection, and that's that's important that we protect Mars, but it creates these additional burdens on these missions, which some are justified. But when it comes to the moon, we want to put enough that we do things responsibly, but not so much that we stifle this ecosystem, which is just getting off the ground. At the top of my head, I'm not sure. I'll have to go back to look at the exact figures on the estimates for water ice, but we have conducted market analysis on how much water ice exists from a few different firms, and have a pretty good understanding of that.
Fantastic.
Thank you very much for the presentation. I forgot to thank you at the beginning.
No, thank you.
Wonderful. Patricio Gallardo.
Hello, I'm Patricio. I'm from Argentina. I'm a physics student. I think of first of all, thank you for the presentation, and I would to know about once the moon rover explore the floor and collect the information, what was the next step for the mission's moon value?
Great question, Patricia. So the easy question is for those first couple missions, which are our first steps into this larger world. The missions will have a lifetime duration. We don't think will be longer than 14 days. And the reason that goes back to lunar night and the difficulties with lunar night survival. These rovers are so small that they do not have the battery or the thermal capabilities to keep themselves alive, or likely will not throughout lunar night, because they don't have, unlike the U-22, the Chinese rover, that has a radioisotope heater unit, an RHU, that is able to power it and keep it heated in a way that our rovers will not be able to. So from a mission perspective, we think we're going to get 14 days of really solid science and exploration and learn a lot of lessons that we're going to be able to apply to future missions. Eventually, we want to get to a place where we have perhaps docking bays in which rovers are able to stay heated underneath the lander, or just like your phone is able to charge through inductive charging, perhaps do that with these smaller rovers as well. But yeah, that's basically it. It's gonna be 14 days, and then we'll move on. Our larger lander, we are intending to survive. We are intending to survive lunar night, so that's something that we're pretty excited about as well.
Do you have time for a couple more questions?
Sure.
Yes.
Yeah.
So Shayla, please go ahead.
Hi, good evening. My name is Shayla. I am an electronics engineering student at Universidad Tecnológica Nacional in Argentina, and also a law student. I am working at the Connecting Worlds team, and I would like to ask you about localization. Taking into account there's no GPS available in the moon, we would like to know how does the rover do to know its own location when it is already on the moon?
So great question. So a lot of you're right. So without GPS, a lot of the stuff we can do is with kind of general reckoning, knowing where the lander is and its orientation, and we're able to queue off of landmarks around it to find that positioning. That's something that we're currently looking more into. It's not so much a problem when the rovers only travel a couple hundred meters away from the lander, but when you start looking at more long duration treks, localization is a much harder problem. I believe ESA just put out a solicitation for an enhanced using GPS signals from Earth in conjunction with other satellites in high orbits to create that, even though it'll be much fainter, create that positioning and timing. Another option would be satellites in these frozen orbits as well. So there's a NASA mission called Capstone, which is being that is currently being developed by for a launch in the next year or so. Maybe it's later this year. I think maybe next year, and that is also testing that some advanced lunar PNT as well. But you're right. That's going to be a very important thing moving forward. When you look at these longer these rovers that are anticipating hundreds of kilometers or tens of kilometers journeys.
And finally, Tomas, last question.
Thanks, Ignacio. Thanks for the talk. It was very well. I'm Tomas Coronel. I'm a mechanical engineer, and I'm working on enterprise at the space. That his name is Skylum. And I want to ask you if you say that in the second step, you have a rover that is between 5 to 10 kilograms, and in the competence of open space, our rover is lower than 2 kilograms. How is your percentage of the subsystems of your rover? Because we have to try to do the same, but with 2 kilograms, and it's a big question and a project to do that. Thanks.
Yeah, it's pretty challenging to shrink the rovers. So I do not have off the top of my head know the exact numbers of what percentage the rover subsystems are broken out, or what the rough payload is, because the rover design in some senses is still evolving. That can generally change. I would say, I think roughly half. I don't want to, but don't quote me on that. I don't want to overstate it. So I think we're generally looking at, a 10 kilogram rover have something, in the neighborhood of maybe 3 to 5 kilograms of payload, but I don't think I know that exactly for sure. I think for you, when you're looking at smaller rovers, like there are the 2 kilogram, you're saying like it's difficult to kind of miniaturize at that 2 kilogram level?
Yes, because only on the batteries you have almost 1 kilogram, because it's a packet that you can buy on the market, and we can't do the whole improve of the technology for ourselves.
Right.
But Marchel, if you tell us that you'll take us for free, we can do a rover for a 5 kilogram rover.
Boom, done. Yeah, that's a good. So that's that is a. We certainly, we feel that also in the. You look at the size of the lander. This lander is, and you saw pictures of it. We have similar problems with fuel, right? Our lander is about 12 feet high, the size of an SUV, and our payload capacity is, and it's not just a problem, our payload capacity is 30 kilograms. Even though our lander weighs substantially more than on the order of thousands of 1,000 kilograms, or a bit more than 1,000 kilograms. And it's the same problem with rockets as well, right? For the Saturn V, 99% of its mass is fuel. I think there are no quick answers to it. It seems like even if you were able to engineer your batteries to be more efficient, there's some fundamental energy density problems that you're having with your lithium-ion batteries that you probably, there's no magic way to get around it, I think. But that's why it's such an interesting problem, right? Like, how can you then, how does that drive other aspects of your architecture? Like, if you're stuck with the 1 kilogram batteries, what decisions do you have to make at other aspects of your rover to hit your weight limit? And that's kind of the magic of systems engineering. And that's why I know it's very hard, because I watch other people do it and I say, man, I couldn't do that. That seems too difficult.
But at the same time, you have 1 kilogram micro rovers, right? In your fleet.
So yes, yeah. So we're currently looking at micro rovers that are on the kind of the order of less than 10 kilograms, single digit kilograms. We should have some more information about that here in the coming weeks. Yeah, that's something that we're looking at.
Fantastic. Marchel, we could spend probably another hour. I can think of 10 other questions that I could ask you, but this was incredibly generous and fantastic. Really an outstanding presentation, and all the answers that you gave. It was a feast for us. Thank you very much for your generosity and the insights, and just being able to talk with other people who are doing this kind of work and are crazy enough to venture into the future of space but you're doing it at another scale, and it's a luxury for us. So thank you once again. Congratulations for everything that you're doing. Just so that everybody knows, this company started with a group of people who decided to participate in a competition called the Google Lunar X Prize, just like other lunar exploration companies that are ongoing today. So big things can start like that. Yeah, you want to make
it's a key. I mean, that's a key point. I mean, you and I, and you know, that's something that you know, should be noticed, that this all started as an idea in someone's apartment, and it has grown into this really multinational, large, you know, massive effort. But everything started so things start so small, and at the time, you know, you're, and this is all before I was with the company, but they ran very lean, and the odds were against them, and they persevered because they believed in the mission, and we've been pretty successful. I've also put my email in the chat, so please feel free to reach out with any questions, or so you know, please don't hesitate to reach out as well, or connect with me through LinkedIn, because I've really enjoyed speaking to you all.
Thank you very much. I hope that this is the first of more opportunities then. I think that we all enjoy really, I mean, all the people who are mentoring these teams are really enjoying sort of the adventure and what they're doing. They're doing very serious work. Hopefully at some point, maybe we can have an interaction where you can see the kind of work that they're doing. I think that you would enjoy it as well. And they're making amazing progress. So, but again, today it's really a big thank you. And yeah, just it was amazing.
Thank you very much, Ignacio. I thank you very much for the time, and looking forward to great things from your organization.
Thank you very much.
See everyone.
Thank you, Marchel.